Okay, hi everyone. We are doing day 2 notes for topic 3 today, and you'll see here actually that I split the notes. It's going to be 2 pages, but I split them into separate titles because I just feel like they're obviously related, but kind of 2 different concepts. So on page 18, which would be the left-hand side of today, is relation versus function, and then page 19, which will be the right-hand side of today, is modeling with functions. Okay, so here is page 18, which is relation versus function, and again, you can write down both dates if you want, or just the date that your class is on, and the learning target is that I can identify a function from different representations. So remember, a function, or I should recall right here, a function is a special type of relation. So it's kind of like a subset, right? It's still included. Just how an apple is under the umbrella of all fruits. It still is identified as an apple, but you couldn't just pick up any fruit and say, this is also an apple, okay? So it's a special type of relation. And this is a function is a relation that has each input go to only one output, okay? So we're going to go back and refer to that over and over and over again until it sticks. The input, you only look at the inputs and see where they're going, and they're only allowed to go to one place. And again, think of the Amazon example. It relates to predictability. We need to be able to say, when you input this specific thing into a function, we can predict the output will always be blank. If there's more things coming out than that, then it's not going to be a function. Okay, and then a little extra thing today that you will need for identifying functions is a vertical line test, or VLT, because you know I like to abbreviate. So, a vertical line test. Firstly, we need to identify that on a graph, a vertical line represents a single input. If you think about it, it's because it passes through the x-axis in one place. So it's an x value, okay? Now, you slide this vertical line back and forth over your graph. And if at any time the vertical line touches the graph in more than one place, so that means that the curve or line or whatever that's on there, your vertical line passes through at multiple locations. That means it has more than one output, okay? So that would be a single input going to more than one output. So then the phrasing we would use is, if that happens, we say that the VLT fails, or vertical line test fails, right? And it's just a relation. So it's still a relation, but it's not actually a function, okay? Now, I know that this seems a little complicated and wordy, but we're going to go over in an example, 2 examples, and it will make more sense when you see it in action. You'll be like, oh, okay, but just realize, I want you to remember, a vertical line represents a single input because it crosses the y or the x-axis in one place. Okay? All right, so now what we're going to do is create a table, and I made this table go down the rest of the page, the whole thing. Notice that I made this column over here really, really small. Please do that. And we're going to, again, explore, just like the title says, things that are just a relation, meaning that one input or multiple inputs go to multiple outputs. Okay, it's not predictable because you're going to have at least an input that has a couple different outputs, and so you never know what to expect. And then over here, we're going to look at functions, which is when each input only goes to one output, okay? So we're going to use this table and look at multiple representations from last chapter, right? So we're going to start with a set of points. So if you want to copy this all down, you can hit pause and then continue with me in a second. Okay, so see that I've added my first section here, and that's a set of points. So this is one way to represent a relationship, is it's just a set of ordered pairs, right? And then curly brackets to show that it's a set, right? Because we learned that for domain and range. So notice I have 2 examples here. I'm going to start with the just a relation side, okay? So the points here are, let me kind of zoom in for you. Oopsies. Negative 3, 4, 2, 1, negative 1, negative 1, 2, negative 3, and 4, 0. Now, what I want to do is actually turn this into function notation. The idea with function notation is if you can use function notation for everything, then it's a function, right? Because it's called function notation. If you can't, then it's not a function, it's just a relation. So what I mean when I say I want to use function notation, and I'm going to abbreviate using FN for function notation, okay, means I'm going to just call it the function f. Remember, you can give it whatever name you want. But here I have f of, and then you put the input, which is negative 3 for the first point, equals 4. Now, I'm just going to go through and skim and see, are there any other times that there's an input of negative 3? So here is one. We just did this one, so I'll put a check mark. 2, that's not negative 3. Negative 1, that's not negative 3. 2, that's not negative 3. And 4. Okay, so far, this is good. We like this. Okay, because we know that it will always be predictable. Whenever the input is negative 3, the output will always be just equal to 4. Okay, then we go to the next one, 2. So f of 2, okay, because you put the input in, equals, and then for that point, that's a 1. Okay, but now I'm going to go through and scan and see, does this input ever occur again? Okay, because you don't want to just do it twice and not think about it. So here, this input's negative 1. No. This input is also a 2. So that means that when the input is 2, we also have an output of negative 3. Well, wait a second. Here, let me do an arrow with this one too. That means that when I have one input, that is 2 outputs. That is not good. Okay, because we do not want multiple outputs. So the bad thing here is that there are 2 outputs. And we would say, obviously, it wasn't going to be a function because it was in this column, but we know that x equals 2, because that's the input, right, has 2 outputs. Oops. So we know it's not a function. Okay? So, not a function. So that's why, because when something works for function notation, for every input, you're just going to get one predictable output. But in this scenario, we had this problem because we had the input 2 occur twice, and it gave us 2 different outputs. Not predictable, not a function. Okay, think about a function like a machine has a function, as in it performs something. If it does this, like if it performs in this way, that's good. Here, this is not performing in the way we want. Think about the vending machines. If it gave you 2 different drinks, you would be upset. You'd be like, listen, I pressed that button. I want chocolate milk. I'm not happy with apple juice. Okay? Okay, so now let's look at this side. So now I have, again, some points. I have negative 2, 0, 3, 3, negative 3, negative 1, negative, or 2, 0, and 0, negative 2. Okay, great. So again, I'm going to do function notation. Okay, and I'm just going to start at the beginning. So f of negative 2, so my input, because that's the x value, equals 0. And then I'm just going to go ahead and skim really quick to see, does this input occur again? So I did this one, so I'm going to give a check mark. And then 3, negative 3, 2, 0. 2 is not negative 2. You are fine. Okay, so good to go. That means good. Then we have the next one, f of 3 equals 3. And I'm going to give it a check mark because I just did it. Now, again, we need to check to make sure this input does not occur again. So negative 3, not the same thing as 3. Okay, guys, if it's a negative, they're literally not the same number. Okay, so don't make that mistake. 2 is not the same and 0 is not the same, so we're good. Then we do the next one, f of negative 3 equals negative 1. So that's good to go, and double check Are either of these inputs the same as this? 2 is not the same, and 0 is not the same. Okay, down to 2 more. So, oops, smiley, smiley, those are good. And then we have f of 2 equals 0, which is that one. That's good because, again, this input is different. And then lastly, this one, f of 0 equals -2. Okay, and that again is good. So if you look here and we look at each of these inputs, notice how each one is different. Okay, we have a different number every time because if you accidentally do it twice, that's not good. And notice that every single one of them only has one output. This input goes to only this place. This input only goes to this place. This input. So it's like a working vending machine. Each one only has one output. It just gives you the one drink you want. So each input has only one output. Okay, and that makes us happy. So if you ever have this where an input is going to multiple, then no, it's not a function. Here, if each one goes to its own not its own location, goes to one location. Because look, notice how these two give you the same thing. That's okay, because remember, sometimes you go to a vending machine and C1 and C2 both give you Snickers. That's okay. What you don't want is if you do one input that you get unpredictable outputs. So it's okay that they go to the same place. All right, so I'm going to go ahead and put a line under that, and our next section will be about maps. Okay, so maps. Maps are when you have like a grouping of the input or x's and a grouping of the output or y's. But notice how under here I wrote domain and range, and I have this for both, by the way. And that's because I'm actually using these points from above, and I'm following the rules for roster notation, for domain and range, which means for this, I pulled all the x values and put them in numerically increasing order, -3, -1, 2, 4, and no repeats. So notice that if we looked at all the x values up here, 2 repeats, I didn't repeat it. Same thing over here, the numbers increase and there are no repeats. So that is a rule if you're going to make your own one of these, okay? Then what we do is we use arrows to show or map which inputs go to which outputs. So from up here, -3 goes to 4. So what I do is I start at -3 and I draw an arrow to 4. Okay? 2 goes to +1. -1 goes to -1. And 2 also goes to -3. So I'm going to come back to 2 and do that. And then lastly, 4 goes to 0. So 4 goes to 0. Boom. Okay? And there you go. Now, how does this help us with domain and range? Well, not domain and range, I'm sorry, functions or not functions. Well, we want to look at our inputs and where they map. So again, if you are following a map, you want to end in one location. Okay, this is not Harry Potter. We don't want to be split into parts. So here, -3 goes to one place. Good, meaning an input has one output. -1 goes to one place. Good. This input has one output. But then notice here how 2 splits off and has 2 separate outputs. That's not physically possible. If we were to literally follow a map, it would not be possible to go down these 2 paths at the same time. Okay? Not a thing. So, again, this means that it's not a function. It's still a relation, but it's not a function because this one is going to go to 2 outputs. So what we want to say here is that, again, because this is my x's and my problem is 2, x equals 2 goes to 2 TWO places. So again, that makes it not a function. All right, so if anytime this one splits, that's fine. Or it's not okay, it makes it not a function. Because you're always going to want to go back. I'm going to make you tell me the definition a million times. It means an input goes to multiple outputs. That makes it not a function. For a function, the input can only go to one place. So again, let's look over here. Again, I wrote domain and range under because what I did was found all the x values, put them in numerical order, and didn't repeat anything, and then found all the y values, put them in numerical order, and then didn't list any repeats. Okay, so now we're set up to do this. So if we go up here, you can see that -3 equals, f of -3 equals -1. So that means that my -3 needs to map to -1. Okay, and then -2 goes to 0. And then 0 goes to -2. And then +2 goes to 0 as well. And then lastly, 3 goes to 3. Okay, now notice that -2 and +2 both go to 0. That's okay. They can do that. Remember, it's the two buttons on the vending machine giving you the same treat. That's okay. Or if you think of it in a mapping sense, your friend and you both start at different locations but end up in the same location. That's okay. What's not okay is you physically being one person and splitting yourself into parts to go to these two locations. That's not okay. So if we look at this, this is a function because each x maps to one place. Each input, or x, I'll put that in parentheses, goes to one place. Okay? Goes to only one place. Again, they can end up and hang out together, or if you have a vending machine, my dream vending machine is every single button gives you Reese's Cups. I'm so for that. And that's okay because I know exactly what I'm going to get. The problem is when the function or vending machine is broken is when you push a button and you never know what you'll get. That's not good. Okay, you call the vending machine company. Okay, great. So there's maps. That's how you tell from a map. Now the next one's going to be tables, and then the last one will be graphs. All right, so now we're on to tables. So tables can be in any random order. Remember, it's not always nice and perfect like we want. I'm going to use the map to draw it. You can also use the points from above. But here, my first x value is -3, and it goes to 4. So make sure that you write the correct thing across from it. Don't just write these numbers and then those numbers. Then I have -1, which maps to -1. So that's the output. Here I have 2, and one time it goes to -3, and then I'm going to do 2 again because sometimes it goes to 1. And then lastly, +4, which goes to 0. Okay. So again, notice here that I have input, the same input, having 2 different outputs, which is not okay. So that is your cue in a table, is if you ever have multiple inputs, like repeated ones, that have different outputs, then that would not be a function, right? So here we have that the input x equals 2 repeats with 2 different, which I'm going to abbreviate to diff, sorry I didn't have enough room, outputs. Okay, so again, always think of predictability. This is not good enough because the 2 has 2 options for outputs, which we don't like. Then over here, we'll do this one. So again, we'll start with -3, which goes to -1. -2 goes to 0. 0 goes to -2. 2 goes to 0. And 3 goes to 3. Okay, So now notice if we look at the inputs, none of these repeat. Okay, so that means -3 goes to one place, -2 goes to one place, 0 goes to one place. And you might think, wait, Miss Azor, look, 0 occurs twice over here. Well, remember, that's okay. You can have the outputs repeat. You cannot have the inputs repeat. Okay, so it doesn't matter if outputs repeat. We only care about inputs. Okay, and again, I just like to think of it as a machine. You're inputting something, okay, and sometimes if you put in two different inputs, the same output will happen, and that's okay. What happens is if sometimes you input, a function, and then a bunny pops out, and then the next time a panda bear, then that's not predictable, and we don't like that, and we'd say, who broke our function or machine? Okay, so now I'm going to put a line under this, and we have graphing, and then we'll go on to the next thing. All right, here's the last representation for functions versus not a function. So all I did was take the points from the table and plot them. Okay, so it doesn't matter, this will apply to any graph you see, even if it is continuous, but this happens to be discrete, but I think it's kind of good to look at discrete. So what we do is each time you draw a vertical line, that represents one input, because it will cross the x-axis in one location. So for example, I'm going to draw a vertical line here, and this represents an input of x equals -3 because it is back 1, 2, 3. And notice how it only hits at one place because that is the one output. -3 does only have one output, and it's 4. Okay, then here, if I put a vertical line through this point, again, this is x equals -1, and again, it only hits in one spot because -1 only maps to one place as well. Okay, so it's showing you that this is an input, and the every time it hits a point or the graph, if it's like a curve, that represents outputs. So then we get to this one here. Okay, and this is x equals 2, which we know from our other stuff that that's our problem. Because look here, it hits once, twice. And what that means is that when the input, because this vertical line represents this input, when we have an input of 2, you end up with 2 outputs. You have this one where the y value is 1 and this one where the y value is -3. So that represents 2 outputs for one input. So that's what I meant about the vertical line test. So these are vertical lines. Sometimes what I like to do is just take my pen and kind of slide it vertically across and see what happens instead of actually drawing them. But there's our problem. So what does this mean? The vertical line represents one input, right? Vertical line represents one input, and it hits, I guess I should draw an arrow because I'm referring to this line, hits 2 points. That means it has 2 outputs. So again, not a function, obviously, because we've just used the same points every single time. But the vertical line represents one input, and if it ever hits your graph, and again, if your graph is a curve, it can still hit a curve in multiple places, right? If it ever hits it in multiple places, that means that there's lots of outputs for the one input, and that's not okay. Whereas if we come over here and really quickly do a vertical line for each of these, and I'm going to see how one is literally on the axis. I kind of just drew the, oh, it's kind of hard to see on the video. Kind of make it thicker lines there. So then notice how every time I have an input, I drew a vertical line, and every single time it hits only in one place, one place, one place, one place, and one place. So every vertical line only crosses up one point at a time, which means it has one output. Okay, so there will be a video for this in class if you need to watch it to kind of help out. But what again this means is each vertical line only hits one point, and in parentheses I'm going to put output, because remember that those mean output, one output, at a time. And since each input only hits one output, must be a function. And there you go. So there are the different types of representations and whether they're just a relation or a function. Because remember, all of these on this left side are still relations, but they're just not functions. Okay, so remember that this is same day of notes, but I'm just giving it a new title and a new page. So I'm on page 19 now. The title is Modeling with Functions, and again, you can just pick whichever day your class actually is. And the learning target is that I can write a function rule for a problem situation. So to model, think about making a model of a house. You're making like something that represents it. That's what we're going to be doing. We're going to make an equation that represents a situation. We're modeling. That's what it means by that, okay? So first things first, remember we've done this before. A function rule is a symbolic representation, so think of like the last unit, but we use function notation, which I'm going to abbreviate using FN again, okay, for fun. And then I have something that I want you guys to sign. So parenthetical promise. So parenthetical means parentheses, right? And a promise means that you're going to vow to do this for me. This is super duper important. It says, I promise to always use parentheses when substituting values into algebraic expressions. Okay? Because if you don't do this, you can compute the problems wrong, especially with negatives. Okay? So I promise to always use parentheses when substituting values, which means numbers, into algebraic expressions or equations or whatever. And we're going to be doing that a lot this unit. Then notice I have an X with a line. That is for your signature. You need to sign this before you turn it in to Canvas. Sign it and then take a picture, okay, of the whole thing. But you know what I mean. Because you are promising that to me. You won't get full points if you don't do it. All right. Now, I'm going to do an example. And the example is about roses. We're going to do a lot with roses next class. It says Roses for You, which is a company I made up, sells roses for a service charge of $40 plus 60 cents per rose. Find the function rule. Okay, so we want to model this situation with a function rule. So first things first, I want to look at what is happening. So it says a service charge. So a service charge would be like normally if you buy roses, like get them shipped to someone, there's going to be a service charge, and $40 is actually not unreasonable. So this service charge of $40, this is the same all the time. It doesn't matter if you buy one rose. It doesn't matter if you buy 100 roses. That $40 is just the fee. It doesn't give us any conditions, which means that this is constant. Okay, so that $40 is constant. It's not going to change. Then it says plus 60 cents per rose. Well, the 60 cents doesn't change, but that amount will change depending on how many roses you buy, right? Again, if you buy one rose, then it's just 60 cents. If you buy 100 roses, then that would be $60, okay? So then this one, sorry, I wanted to do it in a different color. This will change depending on how many roses, right? So we would say that this is changing, or as we learned from the last notes, variable. So notice how I'm getting the two parts of my equation or function rule kind of set up. This part will be a constant, which is just a number without a variable, and this part will have a variable because it can change. Okay, so I'm going to pause and set up a table real quick, and then we are going to do some stuff off to the side. So give me a second. Okay, so notice now I have number of roses. I have everyone's favorite, the process, but I actually promise the process will be easier than doing it with figures and concrete models. FN stands for function notation, and then lastly, total cost. And notice I put a dollar sign, and that's so that I don't have to write dollar every single time. Okay, so it's normal. It's kind of like our normal table, except I added in function notation there in the middle. And then over here I wrote defining variables. So you kind of have two options when you have variables. Sometimes the problem tells you, hey, use this letter and this letter, and you just have to use them because they tell you to. The other option is, in this case, they don't give me any, which means I need to pick. But you can't just pick and pretend like the person who's reading your work, aka Miss Azor, knows what you're talking about. You need to tell me what they mean. So defining means like how you define a word, you're going to define what the variable means. So I'm not even going to be very clever here. I'm just going to have R, and that represents number of roses purchased. Okay, and then C is going to be total cost. So now, everyone should know when they come over here that I'm going to put it in the last column. Give yourself space. I think I used 8 lines. Okay, R represents or is the general representation for number of roses, and cost is C. Well, how do I know what goes in for function notation? Is it going to be R of C, meaning R parentheses C, or C of R, where it's a C and then parentheses around the R? Okay, how do we figure this out? Well, we need to determine function notation. Determine function notation. Okay. So here is the dealio. I know the independent and dependent variables, right? Because they are in my table. The independent variable, it always comes first. The dependent variable always comes second. Easy peasy lemon squeezy. Okay, so I'm going to write a dependency statement. And remember, a dependency statement is that the DV depends on, oopsies, there we go. And then the IV comes second. Okay, so here's what I'm going to do. I'm going to write this out. DV is total cost. I'm just going to abbreviate it to cost depends on number of roses, and I'll just leave off the whole purchased because I'm trying to make it short. Okay, cost depends on number of roses. Great. Then last time we learned that we can switch out depends on for is a function of, and we just keep everything else the same. So cost is a function of number of roses. And I'm just kind of squeezing that in there. Okay. Then what I'm going to do is replace these two things with variables. And I already have the variables because I defined them up here. So cost is C, is a function of, and then R. Okay. And then once it's like this, it's actually really easy because now we kind of just make it go C. And then remember, is a function of, or C of R, means that the of R means the R is in parentheses. Okay? So there is my, what's it called? Function function notation. And then I'm just going to take that and put it in here, C of R. Okay, and that makes sense. The cost, total cost, depends on the number of rows you buy, or is a function of the number of roses you buy. Okay, so there you go. Now we figured that out. Great. Okay, that was actually kind of the tricky part. From here, we're just going to do some work and figure out what the process is. So let's pretend we're just buying one rose. Start small. It's not a big deal. So remember, the service charge is always a constant fee. They will never change it. And since it's a constant, it won't have a variable, right? So 40 is my starting amount. Plus, and then I have 60 cents per rose. Okay, well, firstly, don't write 60 because if this is 40 and that's 60, they'll both be like dollars. I need to make it 0.60 for cents. And then per rose, well, I'm only getting one rose right now. So it's times 1. Okay? So I'm going to skip this over for a second and compute that that's just 40 plus 60 cents. So 40.6. So $40.60. There you go. And then this is C of, and then 1, because the input was 1. Okay, and actually you would say all three of those things are equal. This is not equal to that. Okay, don't worry, that's your input. But this is all equal to each other. Okay, here's the process, which is equal to the total cost, and then this is just the way we write it in function notation. Okay, so 2. So you'll know that this will be C of 2, which again means cost when buying 2 roses. Again, it's more like a code. It tells us more than just C equals 40.60 because it tells me, oh, it's the cost when I bought 1 rose. Let's find the cost when I bought 2 roses. So again, that 40 doesn't change because it's always the service fee plus 0.60, 60 cents times 2 roses. Well, again, hopefully you have a calculator, but that ends up being $1.20. So $40 plus $1.20 is, those are equal, $41.20. Okay, and then when I buy 3 roses, it's going to be $40 plus 0.60 times 3. And again, that's the cost of 3 roses. And what does that actually equal? Well, 60 cents times 3 is actually $1.80. So 40 plus $1.80 is $41.80. Okay, 4 roses is $40 plus 60 cents times 4 roses. And again, that's going to be C of 4 because it's the cost of 4 roses. And then 60 cents times 4 is $2.40. So 40 plus $2.40 is 42.40. Yep, okay, good. And 5 is $40 plus 60 cents times 5, which is C of 5, equals, and then 60 cents times 5 is $3, so that's just $43. Okay, so now if I were to cover up the process and the input, this still tells me like an ordered pair, like you would be graphing. C parentheses 5 is read as C of 5, and it tells me the cost of buying 5 roses is $43. There you go. Now, you also need to be able to work backwards. So let's say I actually already know the cost, and the cost is $45.40. Okay, so that means I have C of something, I don't know what it is, and I have 40 plus 60 cents, again, times something. And that means that whatever number goes here and here goes here. So now I need to work backwards. I know the cost, I need to know how many roses were purchased. And for this, guys, you can just use guess and check if you don't actually know how to solve things yet, and that is fine. If I can open my calculator up, I mean. Okay, and so you would just start doing some guess and check. So the last one we did was 5, so 40 plus 0.60 times, let's say 10. Okay, that's $46. If you can see there's glare, sorry. That is too high. And actually, that's really close. It's just too high. 40, so let's go down one. 40 plus 60 cents times 9. Boom. 45.4, that is the same as 45 and 40 cents. So that means that this number should be C of 9. It's the cost of 9 roses. And we put a 9 in here, which means that number's a 9. Okay? So that's how that works. Then what happens is we want to go to the generalization. So the generalization is the actual function rule, which is what I want to put right here. Okay? So we need to use again, what stays the same every time and what is changing. So 40 stays the same every single time. The 60 cents, 0.60 times something, always stays the same. Then, again, notice that I multiply it by whatever the input is. So if the input is 1 rose, we put a 1 here. If the input is 2 roses, we put a 2. If it's 3, it's 3. If it's 9, it's 9. So if it's R, then, dun, 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 make this R. And those are equal to each other, okay? So it said it wanted us to find the function rule. So the function rule for this is, now remember, function rule is the symbolic representation using function notation. So start with the function notation part, C of R equals, and then do the process, 40 plus 0.60R. And notice I dropped the parentheses because you don't need it. If you set a number and a letter right next to each other, it means multiplication. Okay, so we're going to do one more thing real quick, and that's answer some questions using this function rule, and then we're done for these notes. I did forget that I wanted to say that I want you to remember that this as a whole block is the output. Okay, because think of it this way. Remember, this number up here, total cost, is the output, and that's equal to this, C of whatever. So this must also be the output if they're equivalent to each other. And then the R's here and here are your input. And those need to match, because this to you is the hint of what you plug in, and this is where our parenthetical promise will come in, because if we replace R with a number, we need to replace this R with the same number. So those always need to match. Okay? So it says questions use FN, which is function notation, to solve. So that means that you're going to want to use this. So whenever that happens, I just personally, I'm not even going to read the thing yet. I'm just literally going to copy this into the space. So I have C of R is equal to 40 plus 0.60 R. Okay? Because I know I need to use it, so I'm just going to bring it here. Then the question is, what is the cost of a dozen 12 roses? So I added this because I wanted you to know that a dozen was 12 if you weren't sure already. Well, what they're giving me is the number of roses. And remember, R represents the number of roses. So R equals 12. So what that means is I'm going to make this my input. So in this equation, I'm going to do C of 12 equals 40 plus 0.60 times, that's my parenthetical rule. Remember, I'm replacing the R, so I'm going to do parentheses and then a 12. Okay? That's the parenthetical promise, that you will put parentheses around every time you substitute a number in for a variable. Okay? So now the tricky thing is that people want to do something over here because they think, oh, there's a 12, I need to do something with it. No, you don't. Just leave it alone, because this is actually code, remember? It means cost of 12 roses. Cost of 12 roses is what? Cost of 12 roses is what? So again, if you have a calculator, feel free to use it. We do 40 plus 0.60 times 12. Enter. And that gives me 47.2. But remember, we don't write money as just 47.2. We want to add a 0 because money has 2 decimal places. So there's that. We've done that now. But what does it mean? Well, what this means, remember, it's like an ordered pair. It communicates something to us. And you're going to see that I'm literally going to go across and I'll be able to write a sentence of what this means. So remember, C is the cost or total cost, the cost of, and then this was because of the 12 roses. So the cost of, and you can either write 12 roses or I'm going to write dozen, of a dozen roses. And then equals means is. And then here we have the price, $47.20. And I put the little money symbol. So what this means, this is the function notation for it. This is the meaning in English. The cost of a dozen roses is $47.20. Okay? So now, how many roses can you buy with $50? So again, not even going to worry about that quite yet. I'm going to just copy down the function rule. So C of R equals 40 plus 0.60 R. And then what in the world does this mean and what should I do with it? Well, remember up here, cost is my output. And that means that C of R equals your output. So here, C of R, notice I didn't just write C. C of R equals 50. Okay? And since those are the same, I'm not just going to replace C. Don't just do 50 in for C and leave R. This is a package deal. Okay? Because it means cost of R roses. I don't know what R is, but I'm going to replace all of this with 50. And then keep everything else the same because I want to know how many roses to buy, and that is why I need to solve for R. So again, like above, you can do guess and check. I'm going to solve though, just so that you can see again how to solve. So what we do is, remember you do it in backwards of PEMDAS. So if we're looking at R, we would multiply first and add second. So we're going to do the opposite, and instead of adding, we're going to subtract 40 from both sides. And then 50 minus 40 is 10 equals, and then that's gone, so I just have 0.60 R. And then these are being multiplied, so I do the opposite and divide by 0.60. And I actually do need a calculator for that one. What is 10 divided by 0.60? Oh, 16.6 repeating. So 16.6 repeating equals R. Okay, so what does that mean? So that's the thing, is I can't actually buy 16.6 roses. So how much can I buy with $50? I can buy 16 roses with $50. Okay, and I rounded down. If you're ever not certain whether to round down or up, test on the calculator. If you put in 16, so 40 plus 0.60 times 16, do I go over 50? No, I can afford $49.60 and I'll have 40 cents left over. Then round up and see what happens. If I do 40 plus 0.60 and I round up to 17 roses, that's 20 cents too much. We're assuming I don't have 20 more cents. I only have the $50. So I actually cannot afford the 17th rose. Okay, so that is why I rounded down, because you can't buy part of a rose. So there you go. And that is your answer. Okay, so that is how you use function notation to solve. I hope that this goes well, and I will see you in class.